Welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 2169, titled Count Operations to Obtain Zero. We'll break down the problem, explore potential solutions, and analyze the efficiency of our approach. Let's dive in and get started. In this problem, you are given two non-negative integers, number 1 and number 2. The goal is to find out how many operations it takes to reduce either number 1 or number 2 to 0. In a single operation, you can subtract one of the integers from the other. For example, if number 1 is 5 and number 2 is 3, you could subtract number 2 from number 1 to make number 1 equal to 2. Your task is to return the total number of such operations needed until either of the numbers becomes 0. The input consists of two integers, and the output is a single integer representing the total number of operations required. Let's explore this further with examples. In the first example, we start with number 1 equal to 2 and number 2 equal to 3. The output is 3, and here's why. First, we subtract number 1 from number 2, which means 3 minus 2, leaving number 2 as 1. That's one operation. Next, we subtract number 2 from number 1, which is 2 minus 1, leaving number 1 as 1. That's the second operation. Finally, we subtract number 1 from number 2, which is 1 minus 1, reducing number 2 to 0. That's a total of 3 operations. In the second example, both number 1 and number 2 are initially 10. Subtracting one from the other immediately makes one of them 0, so only one operation is required, and the output is 1. In the third example, number 1 is 0 and number 2 is 5. Since number 1 is already 0, no operations are needed. The output is simply 0. Now, let's review the constraints for this problem. The values of both number 1 and number 2 will always be non-negative integers, and they can range from 0 up to 100,000. This means that our solution must be efficient enough to handle cases where number 1 and number 2 are very large while still ensuring correctness. When considering edge cases, there are a few things to keep in mind. First, if either number 1 or number 2 is already 0, no operations are required, and the output will be 0. Second, if number 1 and number 2 are equal, it only takes one operation to reduce one of them to 0. Finally, for very large values of number 1 and number 2 near the upper constraint of 100,000, the solution must handle potentially many operations efficiently. These considerations will help ensure the implementation is both correct and optimized for all inputs. To solve this problem, we start by considering a brute force approach. The goal is to count the number of operations required to reduce two integers, number 1 and number 2, to 0. In each operation, we subtract the smaller number from the larger one. This process continues until at least one of the integers becomes 0. Here's how it works step by step. First, we initialize a counter to track the number of operations performed. Then, while both numbers are non-zero, we subtract the smaller number from the larger one and increment the counter after each operation. Finally, once one of the numbers reaches 0, we return the counter as the result. This approach is straightforward, but it has drawbacks. The time complexity is proportional to the larger of the two numbers, or O, max, number 1, number 2, because we perform repeated subtractions until 0 is reached. The space complexity is O, 1, as no additional storage is used. However, the main limitation of this method is its inefficiency for large values of number 1 and number 2, as it involves a significant number of subtraction operations, which makes it computationally expensive. To improve efficiency, we can use an optimized approach based on the Euclidean algorithm. The problem's operation of repeatedly subtracting the smaller number from the larger can be reformulated using modular arithmetic. This optimization allows us to reduce the larger number more quickly. Here's the process. We start by initializing a counter, just like in the brute force method. Next, while both numbers are non-zero, we increment the counter by the result of the integer division of the larger number by the smaller one. This step accounts for how many subtraction operations would have been performed if we used the brute force method. Then, we replace the larger number with the remainder of the division. This process is repeated until one of the numbers becomes 0, and the counter is returned as the result. The key insight here is recognizing that the operation described in the problem is mathematically equivalent to the steps in the subtraction-based Euclidean algorithm. By using integer division, we avoid redundant calculations, drastically reducing the number of iterations required. This makes the method significantly more efficient compared to the brute force approach. Analyzing the optimized approach further, its time complexity is O log max number 1, number 2, as the Euclidean algorithm converges in logarithmic steps relative to the size of the larger number. The space complexity remains O1, as it only requires a constant amount of extra space. This makes the method not only more efficient but also scalable for handling large input values. One of the key advantages of this approach is that it minimizes the number of iterations by leveraging the mathematical equivalence between the problem's operations and the steps in the GCD computation. This efficiency allows it to handle large values of number 1 and number 2 gracefully. Given this, the optimized approach becomes the clear choice for this problem. While the brute force approach is simpler to understand and implement, it is computationally expensive for larger inputs, making it impractical in scenarios where efficiency is a priority. By choosing the Euclidean algorithm-based solution, we ensure the strategy is both robust and scalable while maintaining correctness. When comparing the two approaches, there are clear trade-offs to consider. The brute force approach has the advantage of being intuitive and easy to implement. However, it is highly inefficient for large inputs due to the redundant nature of repeated subtraction, leading to a high time complexity. On the other hand, the optimized approach offers significant efficiency gains with its logarithmic time complexity, making it well-suited for larger inputs. The downside is that it is slightly less intuitive, as it requires understanding the GCD equivalence and applying modular arithmetic. Ultimately, the optimized approach strikes the right balance between performance and correctness. By leveraging the mathematical insights of the Euclidean algorithm, we can achieve a solution that is both efficient and scalable, ensuring that the problem can be solved effectively even for large input values. This makes it the preferred strategy for tackling this problem. To solve this problem, we need to determine the minimum number of operations required to reduce two integers, number 1 and number 2, to 0. The operation we are allowed to perform is to subtract the smaller number from the larger one, repeatedly, until both numbers are 0. To begin, the first step is to initialize a counter variable, called operations, and set it to 0. This variable will track how many operations we perform. Next, we use a while loop that continues as long as either number 1 or number 2 is greater than 0. Inside this loop, we compare the two numbers. If number 1 is greater than number 2, we subtract number 2 from number 1. Otherwise, we subtract number 1 from number 2. After each subtraction, we increment the operations counter by 1. This process ensures that we methodically reduce the numbers towards 0 while keeping track of the total steps taken. Once both number 1 and number 2 become 0, we exit the loop. At this point, the operations variable contains the total number of steps required to reduce the numbers to 0, and we return its value as the result. Now, let's look at how we can optimize this process. Instead of performing individual subtractions repeatedly, we can use integer division to calculate the number of subtractions in one step. For example, if number 1 is 10 and number 2 is 3, dividing 10 by 3 gives us a quotient of 3, which tells us that we can subtract number 2 from number 1 3 times in a single operation. This reduces number 1 directly to 1. This optimization significantly reduces the number of individual operations. Furthermore, the problem has a recursive nature. After performing the optimized subtraction, the task reduces to finding the number of steps needed for the smaller, updated values of number 1 and number 2. This recursive pattern repeats until one of the numbers becomes 0. Interestingly, this approach is closely related to the Euclidean algorithm for finding the greatest common divisor, GCD. The sequence of subtractions or divisions we perform mirrors the steps of the GCD computation. The difference here is that we are also counting the total number of operations. This insight highlights the mathematical foundation of the problem. In terms of data structures, this problem doesn't require anything complex. Simple integer variables for number 1, number 2, and the operations counter are sufficient. From a complexity perspective, the time complexity of this algorithm is O log max number 1, number 2. This is because, in each step, one of the numbers is reduced significantly, often by at least half. The space complexity is 1, as the algorithm only uses a fixed amount of memory for the variables. To implement the optimized algorithm, we start by initializing operations to 0. Then, we use a while loop that continues as long as both numbers are greater than 0. Inside the loop, if number 1 is greater than number 2, we compute the integer division of number 1 by number 2, storing the result in a variable q. We increment the operations counter by q and update number 1 to the remainder of number 1 divided by number 2. If number 1 is not greater than number 2, we perform a similar calculation, swapping the roles of the two numbers. Once the loop ends, we return the value of operations. This approach efficiently handles edge cases as well. For example, if one number is initially 0, no operations are needed, and the result is 0. If the two numbers are equal, only one operation is required to reduce both to 0. Even for large numbers, the logarithmic time complexity ensures that the algorithm performs well. This makes the solution robust and efficient across a wide range of inputs. The provided Python implementation solves the problem of counting the number of operations required to reduce two integers, number 1 and number 2, to 0, by repeated subtraction of the smaller number from the larger. The class solution contains a single method, countOperations, which receives two integers as input. First, a variable named operations is initialized to 0 to keep track of the number of steps performed. The algorithm then enters a while loop that continues until either number 1 or number 2 becomes 0. Inside the loop, it checks whether number 1 is greater than or equal to number 2. If true, it subtracts number 2 from number 1, otherwise, it subtracts number 1 from number 2. After each subtraction, the operations counter is incremented by 1. The loop ensures that the smaller number is repeatedly subtracted from the larger one until one of the numbers reaches 0. Once the loop ends, the total number of operations is returned as the result. This solution is efficient, as it directly implements the logic of the problem statement without additional overhead. The use of subtraction ensures that the algorithm terminates in a finite number of steps, as one of the numbers will eventually reach 0. The code is also clean and concise, with clear variable names and minimal use of control structures, making it easy to understand and maintain. This is the Java implementation of the solution to LeetCode problem number 2169, count operations to obtain 0. The logic mirrors the provided Python implementation, where the algorithm iteratively reduces the larger of two numbers by the smaller until one of the numbers becomes 0. In Java, we use explicit type declarations and follow standard Java class structure. The method countOperations takes two integers as input and returns the total number of operations performed. This implementation directly translates the Python logic into Java while adhering to Java's syntax and conventions. Let's begin with example 1, where number 1 is 5 and number 2 is 3. Initially, we set number 1 to 5, number 2 to 3, and operations to 0. As we start the loop, we first check if both numbers are greater than 0. Since this condition is true, we proceed. Next, we compare number 1 and number 2. Since number 1 is greater than or equal to number 2, we subtract number 2 from number 1, resulting in number 1 becoming 2. We then increment the operations counter by 1, bringing it to a total of 1. Now, the updated state is number 1 equals 2, number 2 remains 3, and operations equals 1. We check the condition again, and since both numbers are still positive, we continue. This time, number 1 is less than number 2, so we subtract number 1 from number 2, making number 2 equal to 1. The operations counter is incremented again, reaching 2. The state now updates to number 1 equals 2, number 2 equals 1, and operations equals 2. Once more, we check the condition and proceed because both numbers are still greater than 0. Now, since number 1 is greater than or equal to number 2, we subtract number 2 from number 1, resulting in number 1 becoming 1. Operations are incremented to 3, and the state updates to number 1 equals 1, number 2 equals 1, and operations equals 3. At this point, we check the condition again, and since both numbers are positive, we continue. Since number 1 is greater than or equal to number 2, we subtract number 2 from number 1, which reduces number 1 to 0. We increment the operations counter one more time, bringing the total to 4. Now, the state updates to number 1 equals 0, number 2 equals 1, and operations equals 4. With the next condition check, we see that number 1 is no longer greater than 0, so we exit the loop. The total number of operations performed in this example is 4, which is our final answer for this input. Now, let's look at example 2, where both number 1 and number 2 are initialized to 10. The operations counter starts at 0. As we begin, we check if both numbers are greater than 0. Since they are, we proceed. Here, number 1 is equal to number 2, and since number 1 is greater than or equal to number 2, we subtract number 2 from number 1, resulting in number 1 becoming 0. We then increment the operations counter to 1. The updated state is number 1 equals 0, number 2 remains 10, and operations equals 1. Next, we check the condition again, but since number 1 is no longer greater than 0, we exit the loop. In this example, the total number of operations is just 1, which is our result for this case. Finally, let's examine example 3, where number 1 is 7 and number 2 is 14. We initialize operations to 0. The first condition check confirms that both numbers are positive, so we enter the loop. Since number 1 is less than number 2, we subtract number 1 from number 2, reducing number 2 to 7. We increment the operations counter to 1, and the updated state is number 1 equals 7, number 2 equals 7, and operations equals 1. We check the condition again and continue because both numbers are still positive. This time, number 1 is equal to number 2, so we subtract number 2 from number 1, resulting in number 1 becoming 0. We increment the operations counter once more, bringing it to 2. The updated state is number 1 equals 0, number 2 equals 7, and operations equals 2. At the next condition check, we find that number 1 is no longer positive, so we exit the loop. The total number of operations for this example is 2, which is our final answer for this input. To understand the time complexity of the given code, it's important to see how the operations within the loop affect the two numbers, number 1 and number 2. In each iteration, we perform a subtraction operation, either reducing number 1 by number 2 or number 2 by number 1, depending on which is larger. This means that the smaller of the two numbers dictates how much progress is made in each step, as the difference between number 1 and number 2 decreases by at least the smaller number in every iteration. Now, in the worst-case scenario, where number 1 and number 2 are consecutive Fibonacci numbers, the sequence of reductions resembles the Euclidean algorithm used to find the greatest common divisor, or GCD. The Euclidean algorithm is well known for its logarithmic efficiency, completing in a number of steps proportional to the logarithm of the larger input value. As a result, the worst-case time complexity of this approach is O log max number 1, number 2. When we consider the best and average cases, the time complexity remains logarithmic, but the number of iterations can vary slightly. In the best-case scenario, if one number is much larger than the other, such as when number 1 is significantly greater than number 2, the larger number quickly reduces to a value close to the smaller number, allowing the loop to terminate sooner. Even so, the overall complexity remains O log max number 1, number 2. The average case is similar to the worst case, as the reduction process still follows the logarithmic pattern due to the rapid shrinking of the numbers with each subtraction. Now, for space complexity, the algorithm is highly efficient because it operates in constant space, or O1. The only variables in use are number 1, number 2, and a counter variable named operations, all of which occupy a fixed amount of memory regardless of the input size. Comparing this to a brute force approach, where the larger number is reduced one unit at a time, the brute force method would have a much higher time complexity of O max number 1, number 2. The current approach, by reducing the larger number by the smaller number in each step, is a significant optimization, achieving O log max number 1, number 2. To further solidify why this algorithm achieves logarithmic time complexity, we can draw parallels to the mathematical properties of the Euclidean algorithm. The Euclidean algorithm, which the current approach simulates, is mathematically proven to complete in at most 5 times the base 10 logarithm of the larger input value. This corresponds to a worst-case time complexity of O log max number 1, number 2, and this efficiency comes from the rapid reduction of the numbers in each step. To summarize, the time complexity of our solution is O log max number 1, number 2, while the space complexity remains constant at O(1). This makes the algorithm highly efficient as it leverages the properties of the Euclidean algorithm to minimize the number of operations. Compared to the naive brute force method, which has a time complexity of O max, number 1, number 2, the current approach stands out as a significant improvement, both in terms of speed and elegance. When solving this problem, there are a few common mistakes to watch out for. One major pitfall is not recognizing the GCD pattern. Instead of using efficient operations, some solutions rely on brute force subtraction, which fails to capitalize on the mathematical relationship between the numbers and their greatest common divisor. Since each subtraction effectively reduces the problem size in proportion to the GCD, ignoring this insight can result in poor efficiency. Another mistake is the potential for infinite loops in brute force implementations. For instance, if both numbers are equal and you keep subtracting without a proper termination condition, the program can loop endlessly. Edge cases are just as important. Situations like one or both numbers being 0 or handling very large inputs near the constraints can easily be overlooked. Lastly, brute force methods often lead to poor time complexity, scaling as O max, number 1, number 2, which is impractical for large numbers. Using mathematical optimizations can significantly improve this to O log min, number 1, number 2. Overcomplicating the solution is another trap to avoid. Some approaches unnecessarily use recursion or additional data structures when a simple iterative loop or modulo operation would suffice. Simplicity is key unless complexity introduces clear benefits in efficiency or readability. From an interview perspective, the central insight here is understanding that the number of operations needed to reduce both numbers to 0 is directly tied to their GCD. Recognizing this relationship allows you to minimize steps efficiently. A useful optimization is to replace repeated subtractions with modulo operations. This simulates all required subtractions in a single step, drastically improving performance. Additionally, spotting mathematical patterns like GCD, LCM, or modular arithmetic is a critical skill for tackling similar problems. When explaining your solution in an interview, it's helpful to acknowledge the limitations of a brute force approach and demonstrate how you plan to optimize it. This shows a structured and thoughtful approach to problem solving. This problem is closely related to several others that involve mathematical properties and efficient algorithms. For example, LeetCode 1071, which focuses on finding the greatest common divisor of strings, shares the concept of reducing a problem to its simplest form using GCD principles. Another related problem is LeetCode 1979, which deals with finding the GCD of an array, teaching a similar optimization mindset. While LeetCode 6, zigzag conversion, involves a different concept, it also emphasizes traversing data using mathematical patterns. Finally, LeetCode 509, Fibonacci number, highlights the importance of recursion and optimization in problem solving. Exploring these problems can help you build a deeper understanding of mathematical techniques and their applications across various scenarios. There are multiple approaches to solving this problem, each with varying levels of efficiency. The brute force subtraction method involves repeatedly subtracting the smaller number from the larger until one of them reaches 0. While simple, this approach is highly inefficient for large numbers, with a time complexity of O max, number 1, number 2. A more optimized method is to use modulo operations, where number 1% number 2 simulates multiple subtractions in one step. This reduces the time complexity to O log min, number 1, number 2, making it far more efficient. Another approach is the recursive implementation of the Euclidean algorithm, which elegantly calculates the GCD and operates within the same time complexity. However, recursion may not always be ideal, especially in memory-constrained environments. For such cases, the iterative version of the Euclidean algorithm is preferred. It offers the same efficiency while giving you better control over memory usage, making it a popular choice in competitive programming scenarios. Great job! We've successfully walked through the problem count operations to obtain 0. In this session, we reviewed the brute force solution, analyzed its complexity, and discussed key takeaways. Thanks for watching, and don't forget to subscribe for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!